All right, welcome back. ELE112. This is Chapter 19, Filter Theory. I'm taking a step back into the archives of Chapter 17, and everything I'm going to talk about here applies to Chapter 16 as well. We're talking about filters here. We're talking about filters. If I could spell, that would be great. We're talking about filters. An example of a filter, a coffee filter. You put the beans in the basket, you throw water into the basket. The water that comes through is flavored with the black beans and the flavor. And that's what a filter does. It extracts one thing and keeps the coffee beans up in the basket. Okay? In the electronics world, we have different kinds of frequencies. We have lower frequencies and we have higher frequencies. And the good news is, through the right picking of capacitors and resistors, we can select what frequencies we would like our circuit to pass and which frequencies we would like it to block. Now, just as a primer, as a refresh from Chapter 17, this little circuit that you're looking at before you here is a low-pass filter. It passes low frequencies. Low frequencies always start at 0 hertz. They always start at 0 hertz, and they go up from there depending on how high you want it to go. I could have a low-pass filter that only filters frequencies up to 1,000 hertz, or I could have a low-pass filter that frequencies all the way through 100,000 kilohertz, or 100 kilohertz get through. I could have a low-pass filter that passes 1 megahertz frequencies or less, and 1 megahertz is pretty high. But in the overall scheme of what you're passing, you're going to be passing from 0 hertz to a megahertz. So that classifies it as a low-pass filter. Now, taking a look at the pictures here, like I said, I want this to be a little bit of a primer. This here before you is a DC signal. And you see the DC signal passes through this filter. It has a frequency of 0 hertz. That's about as low as you can get. That is as low as you can get. So what's happening is, if you recall us studying inductors, the inductor is actually a short circuit. It's actually a short circuit at DC. It's like a wire. So the electricity flows, and the 10-volt battery is completely across the resistor, because the inductor is nothing but a bunch of loops of wire, and DC passes, okay? X sub L is 2 pi F L. If my frequency is 0, my ohms are roughly 0, and that's why it passes. Now, as we start to observe the frequency going up slightly, I don't know, this is 1,000 kilohertz in the second example. As we see the frequency going up slightly, then we experience the wave actually passing. It looks like it's about the same size. It's actually a little bit smaller on the right side. It's a little bit smaller. We can't quite see it. And what happens is, the signals, as the frequencies get higher and higher, they start to shrink. So here is a higher frequency sitting in this location. And the higher frequency is what's called attenuated. It starts at 10 volts peak to peak, but ends up at 1.37 volts, causing it to shrink. Now, is the signal actually gone here? No, it's actually still flowing. It's just significantly smaller, okay? Significantly smaller. So if we keep this up and we move down here where the frequency is 20,000 hertz, we doubled it. We doubled it to get here. The signal continues to drop. And of course, as the frequency gets higher, the signal disappears. This is what a low pass does. So in effect, a low pass filter gets rid of your sine wave, your information that's coming in at a given frequency or a group of frequencies is severely attenuated as the frequency goes up, okay? And that produces, that's exactly what we saw in this picture up here. We saw the DC signal complete a picture like this. These are the frequencies, okay? And this filter right about here, it cuts off. It turns off. We talked about it, 0.707 point. It's also known as the half power point because we lose half the power by this time. And it's also known as the minus 3 dB point. This is where essentially the filter is dead down here at the bottom, okay? Now, that being said, this is the response curve, and you'll see that it's plotted with frequency versus voltage right now. And as the frequencies go up, this plot says that the input voltage is never as big as it is at 0 hertz. We pass, and as the frequencies got higher this way, the signal shrunk. If you want to understand from a different perspective, imagine this is a sine wave. You see, the space under the curve starts shrinking, and at some point out here, it's dead. It's not really gone. This signal is never really gone. It just gets really small, and from a distance, it looks like a flat line. So that's a low-pass filter. In terms of a high-pass filter, you see the response curve on a high-pass is completely different. This inductor is a short circuit to DC, so therefore the voltage of a short is 0, and what you see here is 0 volts. Now, as we increase the frequency, the reactance X sub L is 2 pi f. As we increase the frequency, then this side of the equation gets larger and larger, eventually becoming greater than the 100 ohms on the left. Right here, it's 6 ohms. It's almost split. Over here, it's 62, and over here, it's at such a high frequency that what you put in is what you get out. And these filters are great. You could send two frequencies down in through the circuit, one of them very low, one of them very high, and this circuit would pass the very high frequency completely and reject the very low. Very interesting. Here's the response curve for that. And again, if you want to think of it as, the lower frequencies are smaller amplitudes, but out here, what you put in is what you get out. And, I don't know, what do you want to call this frequency here? 10K? Well, I'll tell you what, at 100K, at 200K, at a megahertz, at a gigahertz, this line just stays straight. So the higher the frequency, the better the operation. So I hope you found this introduction useful.